Hi. I haven't checked the mic, but that's for practice by me. And I hope I'm audible. Alright. So here's what I did. What I did was 2 weeks ago I wanted to learn C programming because I wanted to get into systems programming, and I knew C prior because I did a CS course, bachelor's. Yeah. So I gave a cloud prompt. I know somewhat C programming syntax with the help of compiler errors and with proper sequence to cover all the C programming from basic to advanced using simple editor. I'm using Nano right now as simple editor because it doesn't continuously gives me hints. I can use Vim, but I don't know and I don't want to master an editor just now, just because I want to learn manually something, and especially code. If you must be thinking why I'm learning code and AI can do it way better, but I have to understand it and I have to architect it properly. In order to do it, I need to understand what's going behind and what's happening in low level, what we can say hardware level. Okay, so wait a minute. No, I don't know anything about streaming, but I'm streaming because I want to learn, I want to document what I'm learning, I want to see how I can handle different critics about my approach and honest criticism, or if I accidentally did something right for once. So yeah, that's what I'm trying to do here. So already completed it. The cloud gave me the entire list of tasks by phases: foundation, functions and arrays, pointers, memory management, structures and unions, file input output, preprocessor and build tools, data structures, algorithms in C, systems programming, advanced C, and it gave me some kind of hints, little bit hints. So what I'm doing, I'm taking a topic, I'm researching on it, I'm making notes or using AI sometimes if the concept is very important. If I think the concept is very important, that's the key point here. Okay, and I'm trying to learn, then implement, then practice, and then trying to create something out of it. And so that's what I'm doing right now. And honestly, I don't have some big picture right now about what I'm gonna do next, but I'm gonna stick to it. I'm gonna start. Already did some research and learn about memory management. Stack versus heap conceptual model is telling me to draw stack frames and heap region, know where each variable lives. Yeah, so I did some research on it using notebook LM. I don't know what prompt I gave him, but I gave him somewhat like I want to master the memory management. I want to learn stack and heap, and give me the entire document, the entire research for resources, and give me the thing I wanted. So I read it, but I'm gonna start from here. So I will somewhat know, but it will gonna solidate me, and if you guys have any question, you guys can ask me. Okay, so that's what I'm gonna do right now. So what I'm doing, the architectural duality of memory, a comprehensive analysis of stack and heap dynamics in C programming, C systems programming. So the study of memory management within the C programming language represents a fundamental intersection between high-level algorithmic logic and low-level hardware constraint. Yeah. So the high-level algorithmic logic and low-level hardware constraints. So there are gonna be registers and all the hardwares which make up, which due to which the entire programs run and all the things happen behind the scenes. So that's why I'm doing it, learning the C, because it's a very medium level language compared to assembly, but very low level language compared to Python. So that's my key take here. Pardon, I don't have alternate monitor right now, but I'm trying to experiment, I think, on my laptop. So that's why I cannot see the chat every time, or I don't know how to make the adjustments. Yeah, if I stick 2-3 days, I think I'll get the gist of it. So that's good. Wait a minute. I just wanna do one thing. I'm gonna share it to my friend who probably gonna see it, but I don't want him to know that I'm doing it poorly. So I must keep up my game on. Or what we say. I'll be FK for 2 minutes. Pardon the background noises. Right now I have cooler, it's very hot. I'm from India, so it's hot there right now. Actually probably everywhere except some cold places. So yeah. So for systems, programmer mastery of C is inextricably linked to an intimate understanding of how a program utilizes the process address space, particularly the distinct yet complementary roles of the stack and the heap. While modern abstraction layers in high-level languages often shield developers from the nuances of memory allocation, the C practitioner must navigate these regions manually to ensure performance, reliability and security. Yeah, so in C there is no garbage collector. So there is, but it's for actually there isn't any garbage collector. So memory management, if you create a memory for suppose some variable, or if you wanna create a dynamic, you don't know how much space it's gonna take, and still you want to create you can create it, you can create those data, custom data using structs or simple array, dynamic array. But the problem is, you once you created it, it's not automatically gonna free or free the resources. I think that's why it's called free function here. So it's not gonna free the resources by itself, and you have to manually manage those memories if it's in if it's on heap. In heap, I don't know, pardon my English also, because I don't have any solid alimony witness that I speak good English, so pardon my English also. So while modern abstraction layers in high-level languages often shield developers from nuances of memory allocation, the C practitioner must navigate these regions manually to ensure performance, reliability, and security. Yeah. The integration of animations and real-time visualizations has emerged as transformative pedagogical approach, allowing practitioners to observe the transient nature of stack frames and stochastic expansion of the heap, thereby bridging the conceptual gap between static source code and dynamic runtime behavior. Yeah, someone should. So I gave the prompt. I don't know how the notebook LM works. I think it doesn't it's not gonna give me animations by just typing the prompt. I have to use the studio manually to create those prompts. So I wasn't making a YouTube video for that. I was gonna use it for my understanding at that time. I think yesterday or day before yesterday. So yeah. The canonical layout of the process address space. It's all theoretical, I think, so I'm gonna try to explain what I understood, and I think I cannot explain it all, but I think the notebook LM thing did it job very good. Wait a minute, it took approximately nearly 38-39 resources decided and came to the conclusion after that this document is solid. So I'm not gonna trust it, but 100% trust it, but I think it's a solid documentation to learn and get the site. But they say if you don't know, you can't, but if you know wrong, you can learn the right thing anyway. So that's my goal. So the canonical layout of the process address space. A running C program does not perceive memory as a chaotic pool of bits, but as a highly structured layout divided into specific segments. Okay, so the memory is the program does not perceive memory as a chaotic pool of bits. Everything is stored in bits and bytes. Yeah, so but as a highly structured layout divided into specific segments, each serving a dedicated purpose in the execution life cycle. So each segment of the memory segment has its dedicated purpose, and it's very structured way, and the layouts are divided into segments. Okay, and each segment provide a different purpose in the execution life cycle. Okay, the operating system allocates these segments when the program is loaded, typically organizing them by their relative memory addresses to optimize the efficiency of the CPU's memory management unit. This layout is critical because every variable created and every function called must reside in a specific region of this memory map. Yeah. So this layout is critical where every variable created and every function called must reside in a specific region of this memory map. So yeah, I think in terms of complexity complexity of as compared to the nuances of object-oriented programming and stuff, C is pretty much straightforward, but in terms of memory management and systems programming, it's quite a thing to learn. And yeah, so segmentation of memory regions. The memory layout of a standard program is traditionally divided into four primary segments: the text segment, the data segment, the heap, and the stack. So there is four segments. How can I already said it, but I'm gonna create this one. So the four segments. Wait a minute, let me bring out the studio. I'm gonna show you something. Yeah, there is stack, heap, but there are two more segments: the text segment and what's the other segment? The data segment. Okay, so the text segment brings out the text segment deals the code, the source code, deals with the source code, and it is read only. So once the compiler compiles it, and actually the processor brings and adds macros, and then the compiler compiles it, and then afterwards it becomes by assembly. Then assembler processes it and gives back relocatable object files, and that relocatable object file goes down to linker, which links if the program is very big, it links all those all those relocatable object files as it require, and gives the executable. So that this text segment is that executables or what we can say the source code which read. And the data segment for the compiler, it is all the variables and the declaration of functions, not methods. The methods are in object oriented, but we can use it if there is a workaround for it in C. So the data segment, the heap, and the stack. I'm not gonna try to explain because the document is still gonna justify it, but I'm trying to explain that I already read it, and I have somewhat understanding of what's happening. The text segment located at the lowest memory address contains the executable machine code instructions. So yeah, it's the executable, not the source code. After the compilation has successfully done and all the nuances of the compiler stage has been done, the region is typically marked as read only by the hardware to prevent a program from accidentally or maliciously modifying its own logic during execution. Adjacent to the text segment is the data segment, which is further subdivided into initialized and uninitialized. So we are skipping something. This region typically marked as read only. So this is read only, as I said, because once we code, we don't want it to someone to modify it by the hardware to prevent a program from accidentally or maliciously, someone else to modify the executable and add some malicious code or malicious binary to it and its own logic during execution. So to prevent its read only. Adjacent to the text segment is data segment. So after that if we go some higher memory addresses, there are data segments, which is further subdivided into initialized and uninitialized. So the initialized one are straightforward. We specified that there is a variable a which is of kind integer, and it initially stores some data or it doesn't, and afterwards we take the scanf to take the data from user and give it to assigned to the variable. So this is straightforward, but the uninitialized one is a BSS region to store. So the uninitialized BSS regions to store global and static variables that persist for the entire duration of the program's life. So it keeps track of data segment, keeps track of all the variables. Okay, so store global and static variables that persist for the entire duration of the program's life. The heap and the stack occupy the remaining space, and their relative positioning is checking out. Someone stumbled upon the stream, but I don't care honestly. But it would be good. The heap and the stack occupy the remaining space, and their relative positioning is a masterpiece of a architectural strategy. Okay, so the heap and the stack occupy the remaining space. Now the main thing which concerns and which is gonna lay the foundation of the C. Heap and the stack occupy the remaining space, and the relative positioning is a masterpiece of architectural strategy. To maximize the flexibility of both regions and prevent premature exhaustion of address space, they are placed at opposite ends of the available memory and grow toward each other. The stack is at higher addresses and it grows downwards, and there are two pointers, ESP and EBP, extended stack pointer and extended base pointer, which iterates the data and the function callbacks. It's a stack, last in first out. So to maximize the flexibility of both regions and prevent premature exhaustion of address space, they are placed at opposite ends of the available memory and grow toward each other. That's why, to maximize the flexibility of both regions and prevent premature exhaustion of address space. That's why they are at the opposite sides. So that's why it's a architectural masterpiece of architectural strategy. The stack is visualized at the top of the memory map, possessing the highest addresses and growing downward toward lower addresses. Conversely, The heap begins just above the data segment at lower addresses and expands upward. Heap expands upward because it exists at the lower addresses. Okay, so there is a table which makes it easy to keep track of it. Memory segment text, machine code instructions, allocating time, compile time, load, when it allocates, word direction it's fixed and read only, data, initialize and initialize. So my main question right now is, we stumbled upon here uninitialize BSS. So what is BSS? That's what I want to know. It's simply, the stream is for simply I'm learning and trying to do some research, and I already did it once, but here, but I don't know right now. Block started by symbol. Okay, so the block is started. It refers to a specific portion of a program's memory layout, often called an initialized data segment, where global and static variables are stored if they are either not explicitly initialized or are initialized to 0. Okay, either initialized to 0 or doesn't initialize at all, and later maybe they're gonna be useful. So they are, that's why it's block started by symbol, either 0 or something. What is the key characteristics? Automatic zeroing. The system, typically the OS loader or C runtime, automatically initializes everything in this segment to 0 or null for pointers before the program starts executing. The space optimization, unlike the data segment which stores variables initialized with values like int x equal to 10, the .bss section does not store the actual values in the executable file on your disk. It only records the total size needed. Because it's uninitialized, so it is not that important that where it locates, but it stores how much size it's gonna need, which significantly reduces the size of the final binary. Okay, that's why it's space for the space optimized placement. It is located in RAM during execution and usually sits between the initialized data segment and the heap. Example in code. So here, wait a minute guys, I'm gonna just check something real quick, and then afterwards I'm gonna come back. Alright, so where was I? The segmentation of memory regions. The memory layout of a standard C program is traditionally divided into four primary segments: text, data, heap, and stack. We've been through this. Now we're gonna go through this. The heap and the stack occupy the remaining space, and their relative positioning is a masterpiece of architectural strategy. To maximize the flexibility of both regions and prevent premature exhaustion of address space, they are placed at opposite ends of the available memory and grow toward each other. The stack is visualized at the top of the memory map, possessing the highest addresses and growing downward toward lower addresses. So stack grows downwards, means its addresses go from high addresses to low. Conversely, the heap begins just above the data segment at lower addresses and expands upward, which means it's closer to the hardware. Heap is the closer to hardware and possess low memory addresses. Okay. Now here is the table which we were discussing. So text memory segment contains are content types are machine code instruction of relocatable object files or the executable. Allocating time, it's compile time when it's compile or loader when the loader loads it. Its growth direction, it's fixed because the source code is eventually gonna be fixed, and then the executable also gonna be fixed. So it's fixed and it's read only because we don't want any third party or any person to modify the executable while we load it and when we run it. So that's why it's read only. And data memory section, which contains global and static variables and manages their lifetime. So there are two types of variables: initialized and uninitialized globals. So uninitialized are normally called BSS. BSS means what? We are looking into this block started by symbol. Okay, we've gone through this placement. It is located in RAM during execution and usually sits between the initialized data segment and heap segment. So it's not technically in data segment, but there is the contradiction, but it is considered in data segment because it's in the end of the day it's uninitialized data. Okay, so the example, the Gemini gave me the example. What's the example? Global variable, int global variable. It's uninitialized. This one is also uninitialized, static global variable. So these both initialize automatically by to 0, and initialized variable, this one is initialized by 4. So stored in data segment, not basis, because it's not uninitialized, so it's not in basis. Okay, historically the name dates back to the mid 1950s from an assembly instruction used for the IBM 704 computer. For more in-depth details on how compiler handle this section, you can refer resources like this, Geeks or Wikipedia. Yeah, so I'm not gonna go there because we already had some thorough research by Notebook LM. This opposite ends strategy ensures back to heap and stack. Okay, This opposite ends strategy ensures that the program can accommodate either a very deep call stack in recursive algorithms. Yeah, when the recursive algorithm, let me show you something then. Very deep call stack or a very large dynamic data set. It's for heap dynamic data sets in memory intensive application without the regions colliding until the system's total memory capacity is exhausted. So that's why they kept at the opposite side architecturally. The stack, micro-architectural determinism and functionality. The stack is a region of memory characterized by its rigid last in first out operational model, which mirrors the nested nature of function calls in C. Yeah, so what I was gonna show you is where it is, because I'm learning and I'm keeping some source codes and I'm trying to implement enough, so I have some sort of pre-work, the foundational work, but I recently did learn something about stacks and heap and their differences. So that's where we are right now. Recursion. So here it is. Again, so here it's power function, the recursion of the power. Binary recursion. Yeah, so the basic recursion. Yeah, so this is a classical examples which normally come up. I did some pre-work as per the task given, and I successfully implemented some power functions to calculate the power of a based on certain integers. But right now here we are. So if we give Fibonacci, for example, a very large n, the call stack supports, let's check out, this is a Fibonacci. Okay, checks the first one, if n is 0 return 0, if n is 1 return 1, and calculate Fibonacci. So if n is greater than 1, Fibonacci of n minus 1 plus Fibonacci of n minus 2. So the last previous two numbers addition will be the current index. Okay, so pardon me if I did something wrong here. So we're gonna check it out. Okay, I'm using GCC because I don't know Clang right now. We'll eventually cross that bridge too. So it compiles. If I run, yeah, I gave it, I'm trying to calculate hundredth of the Fibonacci, which is quite high. Let's try 40. Look what I'm doing. It's function of Fibonacci, function of factorial. So the factorial is straightforward. If n is greater than 1, factorial will be n times n factorial of n minus 1. So it's eventually gonna sum up and call back. I'm gonna show some notes also after this if you guys want, but right now it's for my learning set, so I already know these things because I already tackled it. So the thing I'm trying to show, factorial of 40, factorial of 40th. Maybe I go wrong. Actually I hard coded it, so it's bound to happen like that. Factorial of 40 is something this. It calculates. The main issue is whether it calculates or not. Let's try 45. We want to, what we want to do is a very deep call stack. So the 40, it's branching 40 to 40, 49th of Fibonacci to 39th of Fibonacci and 38th of Fibonacci. So 45 will gonna do 44th of Fibonacci and 43 of Fibonacci. Then gonna try to add it, so it's gonna branch out, and then gonna it will head back, and the stack's gonna pop up before it's gonna fill. So that's what I'm trying to. We're gonna check deep call stack. Now someone with more skill, and unlike me, I have skill issue, can provide more insights in it. Okay, so for 45 it's taking time, but eventually it's providing the output still. Okay, so deep call stack, so it can handle deep call stack. For my PC, it's handling, my PC is handling somewhat Fibonacci 47. That's pretty basic, but we are trying to do something. So yeah, here, why it calculated it, the program didn't go into very deep call stack and didn't burn out all the memory. The issue is we are using integer, and integer cannot hold. We have to use long if we want to store the higher Fibonacci number. So that's not the issue. We don't care about the output right now. Let's try 49. My question is whether it can calculate it or not, whether we can successfully exhaust all the memory of the stack or not. I think we succeeded in it. No, we don't succeed in it. So in the end it's taking very long time because it's not optimized the Fibonacci. We are not using memorization or something like that. So it's consuming the stack, and it runs pretty much. So why it runs? Because of this their architecture. Okay, so or a very large dynamic data set. So we didn't cross this bridge. Eventually we're gonna cross this bridge. We're gonna implement dynamic data types, probably dynamic array, two-dimensional dynamic array, and probably once we touch the structures and unions, we're gonna start implementing customized data types too, and we wanna to practice on it. Okay, the stack macro architectural determinism and functionality. The stack is a region of memory characterized by its rigid last in first out operational model, which mirrors the nested nature of function calls. We just saw the nested nature of the function call. It provides an exceptionally fast and efficient mechanism for managing local variables and execution context of functions. Because the stack is managed automatically by the compiler and the CPU, it is often referred to as automatic memory. Yeah, it's automatic because we don't have to manually assign the size of the memory while we are creating the variable, and then afterwards once the use has been done, we are not manually freeing the memory we assign to that variable, so it's automatic, but very enhanced and very good structured memory stack. Okay, the mechanics of the stack frame. Every time a function is invoked, the system creates a stack frame or activation record. This frame is a dedicated block of memory that encapsulates all data required for that specific function call, including parameters, local variables, and return address. The return address is perhaps the most critical component, as it tells the CPU where to resume execution in the caller's code once the current function completes. So yeah, the return address is perhaps the most critical, yeah, because we're gonna eventually see some diagrams also, but right now what it's trying to explain is pretty straightforward, and I understood it, so we're gonna continue. The cycle of a stack frame is strictly tied to the function scope. Life cycle of a stack frame is strictly tied to the function scope. When a function is called, its frame is pushed onto the stack. When the function returns, the frame is popped, and the memory is immediately reclaimed for future calls. So yeah, we can visualize it somewhat. The visualizations often represent this process as a vertical pile of boxes. So there are pile of boxes and it's last in and first out. So the last function call gonna execute, evaluate the value, and then if it has return type, it's gonna return, and the return pointer will gonna come back to the second last supposed executable function, I think. This structural rigidity of the source of the stack's speed. The CPU does not need to search for available space, but simply moves a pointer. Architectural support, ESP and EVP registers. ESP is extended stack pointer, and EVP is extended base pointer. So these two help this mechanism to work out, or these two are the responsible for this functionality to work out behind the scene. The efficiency of the stack is largely due to direct hardware support through specialized CPU registers. In the x86 architecture, two primary registers manage the stack pointer and the base pointer, often referred to as the frame pointer. Okay, so the base pointer also referred to as frame pointer. Okay, the stack pointer always tracks the current top of the stack. Because the stack grows downward toward lower memory addresses, pushing data involves decrementing the stack pointer, while popping data involves incrementing it. This is very important thing. We go downwards, the address gets lower, and the stack points to lower region of the memory. The okay. If a program pushes a 4-byte integer onto the stack, the transition is mathematically represented as exp new is exp old minus 4, because integer is what, 4-byte integer. Yeah, the exp is highly dynamic, shifting constantly as temporary values are pushed and popped during the function's execution. Yeah. To provide a stable reference point for accessing local variables and parameters, the compiler utilizes the base pointer. Yeah, so that's where the base pointer come into the play. Once all the functions has been stacked, and when the actual execution has to be started, the base pointer points to the most recent function, or should we say the last function, and it starts its to provide a stable reference point for accessing local variables and pointer. The compiler utilizes the base pointer. At the start of a function, the prologue, the current base pointer is saved on the stack, and the new base pointer is set to the current value of the stack pointer. So internally two pointers points at the same, but the base pointer start when as the execution goes, the base point, this creates a fixed anchor for the duration of the function call. So point if my understanding is wrong or something, but that's what I understood. For example, the first argument passed to the function can typically be found at the base pointer plus 8. The first argument passed to the function can typically be found at base pointer plus 8 byte. Okay, while the first local variable is located at base pointer minus 4. This stable indexing allows the compiler to generate efficient code that does not depend on the fluctuating value of the stack pointer. Yeah, because it as the program executes, it reads and does this thing. So the base pointer points to is the fixed one which points which by which we can locate the next function, and then when the function pops out, the value gonna be calculated based on that. I think I'm talking gibberish, I don't know, but my understanding is limited. I think the function prologue and epilogue. The creation and destruction of stack frames follow a standard sequence of assembly instructions known as the prologue and epilogue. This sequence ensures that the execution environment is preserved across function calls. Prologue. Push base pointer. The caller's base pointer is saved on the stack to be stored later. Okay, so the caller's base pointer is saved on the stack to be restored later. Move stack pointer base pointer. The current stack pointer becomes base pointer for the new frame. Yeah, so once the stack pointer becomes the base pointer, the stack pointer, then what, sub n from stack pointer. The stack pointer is moved downward by n bytes to reserve space for local variables. Okay, so this is the variables, somewhat number of variables, or bytes, the bytes of variables, number of total bytes of the variables which is stored, which gonna be stored. Okay, Epilogue. Move base pointer to stack pointer. Local variable space is collapsed by resetting the stack pointer to base pointer. Okay, pop base pointer. The color's base pointer is restored from the stack. So once it's used, again here the current stack pointer becomes the base pointer for the new frame, and here the local variable space is collapsed by resetting stack pointer to the base pointer. So the stack pointer points to the base point, I think. Yeah. The color's base pointer is restored from the stack. Great. The return address is popped into the instruction pointer to resume the caller's execution. Okay. Visualizing this, so we are not visualizing any of this. So we have to guess and try to do something in our mind. So from next time I'll try to dig up and create a proper animations, or try to find where I can find it and try to learn from there. Okay. Visualizing. These registers movements through animation reveal the elegant handoff that occurs during nested calls, where a chain of saved base pointers allows debuggers and the runtime to walk the stack and reconstruct the call history. This purpose, known as stack walking, is how a debugger provides a backtrace of functions. Yeah. So understanding the stack is very important, and somewhat when the segmentation called or I don't think sometimes overflow or the call stack memory run out from the call because of the call stack. So these things we have to keep in mind and try to understand, because if we don't understand the stack, and this is some very assembly level thing. So it's very essential to understand, I think, if we want to learn C programming properly and try to implement. When the implementation part come up, then we want to see the heap. The entropy of dynamic allocation. In sharp contrast to the stack's automatic and deterministic management, the heap offers a flexible, programmer-managed pool of memory used for data that must outlive the function that created it. Yeah, so why heap is different? Because once the variable create in normal cases in C, once the variable creates its scope is limited to the function it's declared in, or we create the global variables. That's a different scenario, but it gives the global variable can be accessed from any function then. So that's not very good practice to do, I think. The heap is essential for handling data structures whose size is only known at runtime, such as dynamic arrays, linked lists, or large objects that would exceed the stack's limited capacity. Okay. Heap is essential for data structure whose size is only known at runtime. Yeah. When suppose the user types how many articles he wrote. We are taking a survey of a blogger. How many blogs he wrote, what topics he wrote. We wanna take, and he is giving us that information. So in that order, the numbers are not known until the runtime. I think that's the very good example. Dynamic memory management, so the malloc and free, the C standard library. So these two functions are very important to understand if we want to know the basic functionality of the heap. For C, dynamic memory management, malloc and free. The C standard library provides malloc, calloc, realloc and free functions to interact with the heap. When a function calls malloc size, the memory allocator, a complex software subsystem, searches the heap for a contiguous block of at least sizes bytes, marks it as allocated, and returns a pointer to its first byte. Okay. Searches the heap for a contiguous block of. So in heap region, it is the memory allocator gonna search for the that this many bytes of memory segment, memory size. Okay, and then after it finds based on the complex software subsystem, it's gonna allocate it if it finds, and then afterwards it returns the pointer to its first byte. Okay. The programmer bears the absolute responsibility for deallocating this memory using free PTR when it is no longer needed. Yeah, we have to manually free the memory we allocate using malloc or I think calloc. I don't know these functions right now. As you can see, my timeline is quite different. Unlike the stack where deallocation is a side effect of returning from a function, heap memory remains live indefinitely until explicitly released. This manual control is a double-edged sword. It provides unparalleled flexibility but introduces a wide class of bugs such as memory leaks and dangling pointers. Yeah, the memory leaks can occur or dangling pointer. Once we free the I think the dangling pointer is once we free the space, the pointer points to still pointing to something, but that something is not there as we freed it. So it starts pointing garbage value or something. So we don't know what it's pointing. It's undefined behavior, I think. So we have to carefully, if we want to tackle this, we have to carefully after freeing point the pointer, assign the pointer to null, I think. Yeah, and I don't know how, I cannot explain the scenario probably right now, but okay, we're gonna walk into it as we are reading. The role of the program break, BRK and S break. Okay. SBRK. The role of the program break. Okay, so these two. At a lower level, the heap is managed by the operating system kernel. The boundary that separates the end of the heap from the unallocated memory above it is known as the program break. Okay. The boundary that separates the end of the heap from unallocated memory above it is known as the program break. Okay. To expand the heap, the C library uses SBRK increment or BRK address. System calls to request that the kernel move this break further into the unallocated space. So if suppose the heap region, the allocated heap memory is full, or we need some more memory, in order to get it behind the scene as break increment or break address system calls to directly to the kernel, which gonna break further into the unallocated space. which means in short is gonna allocate more memory to heap region, I think heap segment, in order to continuously execute the program. Animations of SBRK show the heap pushing its boundary upward as the program requests more resources. Interestingly, even simple calls like printf may trigger significant heap growth because they allocate internal buffers for standard output during their first invocation. Oh, only for the first invocation, okay. But they do allocate internal buffers for standard output during their first invocation. The return value of SBRK0 is often used by allocators to determine the current end of the heap. Okay, this way we can see the current end where the heap ends. Okay, which address is the last one, I think. We are not gonna do these things right now, as we are just scratching the surface of the theory. Once we're gonna start implementing, then I know necessary syntax. Actually I know somewhat, but we're gonna do systematically, I think. Fragmentation and coalescing, I think I phrased it right, I don't know. Coalescing, because heap memory can be allocated and freed in any order, it is inherently prone to fragmentation, a condition where memory becomes unusable despite being free. Yeah, fragmentation occurs when suppose there the technically there is available, suppose we want to store 8 byte float, okay, and there is available 8 bytes are available in heap segment or region, but it's available in two different intervals, like 4 byte is in some region and 4 byte is in at different region. So that's why that we cannot use it, but technically it's available, but we cannot use it. So that's the condition of fragmentation, I think it is. I'm gonna have to check it. So I'm gonna have to check it. What I'm gonna do, I'm gonna have to cross check it. So let's cross check it for once. Nowadays we don't use fragmentation. I cannot spell everything, bro. Don't expect from me to spell it, but I think I should do. I think float is 8 byte. I don't know this one too. We're gonna do recursion. Four bytes. And what double? It's precision one, double precision, 8 bytes. Ha. So we learn as we go, and I'm learning right now. I'm not trying to explain or smart anyone. Available byte is 1. place and pardon my English. But allocator needs contiguous 4 bytes block to store something like double x. Since the free memory is split into two separate 4 byte chunks, the allocator cannot place double there. So the allocation fails even though 4 plus 4 is 8 byte total free, because memory allocation usually requires one continuous block. This is the core idea of external fragmentation. You can think of it. So there are types of fragmentation actually. This is a condition where memory becomes unusable despite being free. So this is the external fragmentation. There are two types. External fragmentation, this occurs when the total free memory in a heap is sufficient to satisfy the allocation request, but that memory is divided into small non-contiguous holes that are each too small to fulfill the request. That's what I was trying to explain. So that's one type of fragmentation, external. And what's the internal fragmentation? This occurs when the allocator provides a block slightly larger than what was requested, often to satisfy 8 byte or 16 byte alignment requirements, leaving wasted space within the allocated block. Okay, sometimes the allocator provides more than 8 byte or 16 byte, so that way those extra bytes or extra what we can say memory goes unused, I think. So that's internal fragmentation. Alright, so that's how it is. You can think of it like parking space. Two separate bike spots not become one car spot. Even if our total area is enough, the object must fit contiguously. Okay, a simple visualization. Yeah, so that's the visualization we are looking to. I should do this often, but just for you guys to see it, I already imagined it, but in order to make a proper documentation, I think I should do it. There's also internal fragmentation, which is different. For example, you request 4 byte, allocators use 8 bytes. Okay, so this is internal fragmentation. I hope I know somewhat afterwards. Requested 6 byte, allocated 8 byte, unused inside block 2 byte. That wasted space inside an allocated block is internal fragmentation. Okay, and I think there is some concerns regarding 2 raised to, like 2 raised to 2 4, 2 raised to 3 is 8. So I think that that's the reason for internal fragmentation. I think, I'm not sure, but I don't think that's the reason, but I'm gonna just try to learn how, but then I'm gonna eventually stumble why all of it didn't work out, and then I'm gonna go, that's why, because all of this not solid. But knowing something is very important, I think. To combat fragmentation, allocators perform coalescing. When two adjacent blocks in the heap are freed, the allocator merges them into a single large block. Visualizations represent this as removing the separating line between two neighboring free rectangles to create a wider space for future large allocations. Okay. Allocation strategy. There are allocation strategy. First fit. Set mechanism scans for the start for the first sufficiently large block. So there is a way to find the memory which the programmer asked. The first fit does what the scans from start and gives the whatever the first available size the programmer asked to it, sufficient large block. Okay, fragmentation level high, very high level, leaves small holes at the start. Okay, efficiency high, fastest search because it's the first available memory which can be used. Next fit, start the scan where the previous search ended. Okay, so it keeps track of the where we assign uh, suppose x variable and the end of it, and gives right if the next variable can be stored afterwards, it gives the next available space. Fragmentation level moderate, efficiency high, avoids clustering at the start. Okay, best fit, scans the entire list to find the smallest block that fits. Fragmentation level low, minimizes best. Okay, finds the best fit. Okay, so it scans the entire list first and then gives the smallest block that fits. Okay, efficiency low, slowest search. Okay, this is slowest search, but it guarantees the least fragmentation. Okay, the choice of allocation algorithm significantly impacts the performance of multi-threaded applications. Okay, the choice of allocation algorithm. There are some allocation algorithms. The modern allocators like jmalloc, pcmalloc from Google and memalloc from Microsoft utilize thread local caches to reduce lock contention and improve cache locally, addressing the heap slow stigma. Okay, so I get it. They try to catch it and they found some workaround, and I have to know what was the workaround. Traditionally, data reporters and the reputation of being slow because of this problem in multi-threaded program. Many threads all calling malloc free. One shared global heap. Locks everywhere. Thread wait on each other. Okay, so it locks some block of the memory because heap is global. So the malloc and free in multi-threaded applications gonna. Okay, so that's what happened. All right. Older allocators often protected heap structures with big locks. So if thread A calls malloc, thread B calls free, thread C calls malloc. Okay. So thread A calls malloc, thread B calls free, then thread C calls malloc. They may all compute for the same heap lock. So the same address or the same memory they want to contest for the same memory. So that causes lock contention, cache misses, CPU stalls, poor scaling. So what's the workaround? Modern allocators like jmalloc, pcmalloc, memalloc solve this mainly using thread local caches. Per thread per CPU heaps, smarter size classes reduce the synchronization. Okay, core idea thread local allocation. Instead of all threads one heap, they do thread A local cache, thread B local cache, thread C. Oh, they are caching it. So most allocations happen without touching the global heap. Oh, allocation happen without touching the global heap. They cache it and then try to assign. Okay, Example, suppose thread A frequently allocates small objects, cat malloc 64 bytes. Okay. Modern allocator behavior, thread A case, block 64 byte, block 64 byte, block 64 byte. Allocation becomes take block from local cache, no global lock needed. That makes allocation extremely fast. Okay. What happens on free when thread frees memory? Repeat. Instead of returning it immediately to global heap, return to thread local free list. So future allocations reuse it quickly. Oh, so instead of giving back the allocated memory, that memory gonna be used somewhere else in the same thread because it's locally cached. So the heap load gonna be reduced and the lock contention gonna be minimal. Why this heap helps performance? Reduces lock contention. All every malloc 3 needs lock. Okay. Modern, most malloc free are lock free. Huge difference in highly threaded servers, games, browsers. Okay. Better cache locality. If thread A allocates memory, thread A likely uses that memory. So if thread A allocates memory, thread A likely uses that memory. Keeping allocations near the same thread improves CPU cache usage. Oh, CPU caches allow predictable local memory access. Okay. So the heap becomes I think some region of the heap gonna be used by thread A because the cache gonna access that area. Is that the thing or not? I'm gonna ask it. Less false sharing. Without thread local allocation, a thread A and B may modify nearby memory, which causes cache line bouncing between CPUs. Per thread arenas reduce this. Okay, so it draws some kind of partition on heap. I think. Is that a thing? I'm gonna ask it. First I have to read the whole thing. Simplified architecture, all allocator, global heap, one big lock, and all the threads gonna try to utilize the heap. But a modern allocator, T1 local arena and cache, T2 thread 2 local arena cache, thread 3 local arena cache, only occasionally local cache and global heap interact only when the memory is needed. I think that's when. But what about memory waste? Thread local caches can increase memory usage because thread A holds unused blocks. Thread B cannot use them immediately. Yeah, that's what I'm trying to say. Modern allocators combat this with periodic scavenging, cache trimming, decay systems, returning pages to OS. Modern allocators combat this with periodic scavenging, cache trimming, decay systems, returning pages to OS. Okay. Periodic scavenging. So I'm pretty new and I'm trying to learn as recursive way as I go. I'm trying to dig deeper. I should just understand the heap and stack and heap diagram and go on with my day. But I want to learn from day zero and give my best. So that's why I'm trying to document it also in my tone. I think periodic scavenging, cache trimming, decay systems, returning pages to OS. Okay, modern allocators combat with these things. Cache trimming, decay systems, returning pages to OS. Why different allocators? Different allocators optimize different workloads. JML are good for fragmentation reduction, server workloads, predictable performance. Used heavily by databases, web servers. Okay. TC-malloc, very fast small allocations per CPU caches used inside many Google systems. Numalog, focus low latency, NUMA awareness. What is NUMA now? Security features, good real world balance, very modern design. Why heap is slow? Become less true. Old view, heap allocation, OS calls, global locks, fragmentation, slow. All these factors. Modern reality, malloc free often. Thread local pointer manipulation. Okay, so that's why there are some flavors to the malloc and free, I think. Sometimes nearly as cheap as a stack like allocation for small objects. Not literally stack speed, but massively faster than old allocators. Real world impact, programs heavily affected by allocators quality. Oh, pardon. Browsers, game engines, compilers, databases, web servers, AI, times, vendors. A bad allocator can bottleneck the entire application. So we have to use specific allocator, I think, or a specific version of malloc or calloc. I don't know what calloc does, but I have somewhat idea of now of what malloc does. Now back to the question I had. My one question is, does caching creates imaginary partitions on heap? That's the first one. And another one is, what was another one? I think another one was answered, but I have to ask it. What is NUMA awareness? Does thread local caching create a conceptually yes, okay, so that physically not exactly fixed partition. Modern allocators often divide heap management into arenas, thread caches, size, class regions, slabs, spans, pages. So instead of one giant shared heap, global heap, you get something more like thread A, arena A, thread B, arena B, thread C, arena C, or CPU 0 local cache, CPU 1 local cache. These are not strict hard partitions like disk partitions. The allocator is basically saying these memory regions are primarily managed by this thread or CPU. Oh, I was thinking somewhere right in the right direction. So imaginary partition is actually a pretty good beginner mental model. Important detail. The memory still ultimately comes from virtual memory, pages from OS, the process address space. The allocator just organizes it differently internally. Example, suppose allocator get 1 megabyte from OS, 1 megabyte memory from OS. Okay. Internally it may divide like arena 1 gets 256 KB, arena B gets 256 KB, arena C gets 256 global reserve. Okay, so this it might happen like this. Each thread mostly allocates from its own arena. This reduces contention. Why it helps? Without partitioning, all threads modify same allocator method. That's what we are trying to solve from the get-go. So Yeah, conceptually I was right, I think. And that's how it happens. Okay. Leading to locking, cache bouncing, synchronization overhead. With arena thread caches, most allocations are isolated, so CPU's interface fares less. Okay. What is NUMA awareness? NUMA, non-uniform memory access. Okay. So inconsistent the memory access. Okay, non-uniform memory access. It's a hardware architecture used by many servers, workstations, multi-socket systems. Core idea: not all RAM is equally close to a CPU. Example system: CPU 1 RAM bank 1, CPU 2 RAM bank 2. CPU 1 can access its own RAM quickly, CPU 2's RAM more slowly. Oh, hence non-uniform access time. NUMA. Okay, visualization. CPU 1 can access RAM 1 very fast, but CPU 1 can gonna access RAM 2 very slow because it's not CPU 1's RAM. Why this matters? Suppose thread runs on CPU 1, but memory was allocated on RAM near CPU 2. Then every memory access becomes slower. Modern CPUs are incredibly fast, so memory latency matters a lot. Yeah, we are living in technology right now, so I'm trying to learn it, but somebody gonna start learning where I'm learning, so it's very good. NUMA aware allocators. Modern allocators try to allocate memory near the CPU thread using it. Modern allocators try to allocate memory near the CPU thread using it. Okay. This way, CPU, if the memory gonna be utilized by CPU one, so it's eventually gonna stored in RAM one for to reduce the latency. Okay, non-uniform memory access. Alright, this improves cache locality, latency, bandwidth, scalability. Yeah, that's what I'm trying to say. Example: without NUMA awareness, thread on CPU 1 uses memory from distant RAM. With NUMA awareness, thread on CPU 1 allocator prefers RAM attached to CPU 1. Yeah. Less latency. Real world importance. NUMA awareness matters heavily in databases, cloud servers, rendering, scientific computing, AI training interface, high frequency trading. Less important on small laptops, normal desktops, because many consumer systems are effectively uniform memory access. Okay. Simple analogy. CPU's workers RAM warehouses. NUMA unaware worker in Pune fetches tools from Delhi. NUMA aware worker in Pune fetches tools from Pune warehouse. Same tools, less travel time. Okay. Now I understood it. Actually, technically, I should not get in too deep in that, but I want to, because if you see the timeline, there is not it's very shallow time way of going, but I wanted to dig deep and try to understand thoroughly the stack and heap concept and how it goes. In order to understand it, I have to go and do thorough research on it. So some things came from from where is the multi-thread gonna get introduced in my timeline, if it's gonna introduce systems programming, I think. No, somewhere it's eventually gonna be get introduced in our timeline, but If it's not, we're gonna make it introduced. So the next, let's see next. Instruction paradigm, the role of animation in mastery. Yeah, so we're gonna skip it because I asked something different. Let's read it out anyway. Traditional methods of teaching memory management often rely on a static diagram that help capture the temporal shifts and state transitions of a running program. AI augmented and interactive visualizations have bridged this gap by providing real-time feedback that synchronizes code execution with memory layout changes. Real-time runtime visualization tools such as online Python torch tutor with support CLC. User Tech memory layout visualizer online Python tutor. That's it. Let's see. The only tool that lets you usually debug your C code step by step. GDB can do that too. I don't know, GDB had some. There are some big skill issues in my tech stack and knowledge, but somewhat I try to understand it. I'm not gonna use it. So this one, and what's the next? Lucera Tech Memory Layout Visualizer. The MV allows students to step through code line by line. Okay. These platforms provide a dual pane view. One side shows the source code with a pointer to the current instruction, while the other side shows the stack frames and the heap dynamic pool. Consider the execution of the line. Okay, the pointer gonna get size of this much size of integer size means 4 byte. It's gonna 0.4 bytes. Okay. Animation of this event would show a box level PTR appearing in the current stack frame. A new block of memory, for example 4 bytes, appearing in the heap region, perhaps color coded to indicate its allocated status. A dynamic arrow representing the memory address being drawn from the stack variable PTR to the newly created heap block. This visual link is critical for mastering C pointers. It clarifies that the pointer variable on the stack does not contain the data itself, but rather the location of the data residing in the heap. Yeah, that's very important. The pointer does not contains the value, it points to the address where the value resides. Okay. Modifying the value at the pointer, dereferencing the pointer. We're gonna modify the value of the from the point using the pointer. Is visualized as the value 10 flying from the CPU into the heap block targeted by the arrow. Yeah. Cognitive metaphor, backpacks versus warehouse. This is very important one. Educational animations frequently employ metaphors to simplify complex behaviors. A popular metaphor describes the stack as a backpack and the heap as a warehouse. The backpack stack, it is small, fast, and always with you. You can reach in and grab items quickly, but space is extremely limited, typically 1 byte, megabyte. MB. And you must pack and unpack items in a specific leaf order. When you exit a function, you effectively throw away that specific pocket of the backpack. The warehouse means heap it is vast and can hold massive items like large arrays or complex structures, but it is located further away, slower access due to allocator logic and potential cache mixes. You must manually sign out items via malloc, and you must remember to return them via free, or the warehouse will eventually become full. Okay, this I have to we have to keep these things in mind. Okay. Hmm. Pardon my English, anyways. Another metaphor compares the stack to a stack of cafeteria plates. One can only add or remove a plate from the top. Attempting to pull a plate from the middle, accessing the apparent function's local variable, is impossible without first removing everything above it. This reinforces the concept of scope. Variables from functions that have already returned are gone because their plates have been removed from the stack. Yeah, once failure moves, pathologies of the stack and heap. A primary motivation for mastering memory models is the prevention of critical runtime errors. Memory related bugs are notoriously difficult to debug because the crash often occurs far from the original error. Stack overflow, the perils of infinite recursion. The stack has a fixed size which is determined at program startup and generally cannot be resized. A stack overflow occurs when a program attempts to push more frames than the allocated space can hold. The stack has fixed size, which is determined at the program startup. Okay, generally cannot be resized. Stack overflow occurs when a program attempts to push more frames than the allocated space can hold. Yeah, we are trying to do the stack overflow using the recursion function. If when I was running the Fibonacci of 100, if the algorithm is gonna optimize it, eventually gonna give the stack overflow, but it's gonna take some time, so that's why I didn't continue. Or probably it's gonna give me the answer because my laptop is quite good, I think. Not very good, but quite. This is most commonly seen in recursive functions that lack a proper base case or go too deep. In our case, we are trying to go too deep, so that we got to have a proper base case, and we have to optimize the algorithm. That's why algorithms and data structures are very important, which we gonna eventually cover, I think. In an animation of factorial function n factorial, each recursive call creates a new frame on the stack. If n is very large, the frame marches downward toward the heap until they exceed the predefined stack limit, often 1 megabyte on Windows or 8 megabyte on Linux, causing the OS to issue a segmentation fault and terminate the program. The memory leaks, the slow killer. A memory leak occurs when a program allocates heap memory but loses the pointer to that memory before calling free. Oh, that's very dangerous. This memory remains reserved by the operating system but is unreachable by the program logic. Visualizations represent this as a lost block in the heap with no arrows pointing to it. Over time, these lost blocks accumulate, leading to a sawtooth pattern in memory usage graphs. The memory usage rises as the program runs, and while it may dip slightly when the program clears its stack, the heap's baseline continues to creep upwards until the system runs out of memory. Unlike the instant death of stack overflow, a leak is a slow killer that degrades system performance gradually through thrashing and swap usage. Oh, thrashing and swap. Thrashing is when we're gonna use storage instead of the RAM to process something. So that's when the swap usage occurs. Swap usage is the function, I think. Yeah, dangling pointers and buffer overflows. Dangling pointer is a pointer that still contains the address of a memory block that has already been reallocated. If the program attempts to dereference this pointer, it may read garbage data or overwrite memory that has since been reused for a different purpose. Okay. Animations show the heap block being cleared or grayed out while the pointer arrow from the stack still points to that empty space. Setting a pointer to null after freeing it is the standard defense, and it breaks the arrow and makes subsequent accidental use cause an immediate detectable crash rather than silent corruption. Yeah, or someone can use that memory location, that pointer, I think. Buffer overflows on the stack are even more dangerous. If a program writes data past the end of the local array, it can overwrite the return address. Okay, stored in the stack frame. In an animation, this would look like a data stream spilling out of an array box and drowning the return address box below. If an attacker can override this address with the address of their own malicious shellcode, the CPU will jump to that code when the function attempts to return, giving the attacker control of the system. So, buffer overflow are very dangerous, I think. So when we treat arrays, I suppose, and we with the for loop, and we forgot to write the right condition to end the loop, or we don't know the size of the array and we try to iterate anyway, and we go beyond the array. That's when this happens, I think, because the program tries to access the address which it should not access. So that's when it happens, I think, the return address, I think. Advanced system considerations and mastery. As developers transition from basic proficiency to mastery, they must account for complexities of modern architectures, including multi-threading, cache effects, and specialized stack behaviors. Multi-threaded access and cache locality. In a multi-threaded process, each thread is assigned its own private stack to maintain its execution context. This isolation makes stack data inherently safer from concurrent modification by other threads. This isolation makes stack data inherently safer from concurrent modification by other threads. However, the heap is a global resource shared among all threads in the process. This shared nature requires the use of synchronization primitives like mutexes within the memory allocator to prevent race conditions, means trying to access same memory address differently. Which is why heap allocation is historically slower than stack. Cache friendliness is another critical factor for mastery. The stack is a small compact region of memory that is accessed frequently, making it highly cache friendly. Cache friendliness is another critical factor for mastery. Okay, no point to be noted. The stack is a small compact region of memory that is accessed frequently, making it highly cache friendly. The CPU's L1 and L2 caches can often hold the entire active portion of the stack. Once we completed and proved that we learn we're gonna go into computer architecture and learn these caches and somewhat try to get the gist of some of the modern computer architectures too, so that we know some low level things. But L1 and L2 very fast. Okay. In contrast, heap blocks are often scattered throughout physical memory, leading to more cache misses and significantly slower access speeds as the CPU must fetch data from relatively sluggish main RAM. ARM architectures, MSP versus PSP. In embedded systems programming, particularly on ARM Cortex-M processors, the stack model is further refined. The architecture supports two separate stack pointers, the main stack pointer and the process stack pointer. Main stack pointer. This pointer is used for exception handlers, interrupts, and typically by the OS kernel itself. And another process is stack pointer. This pointer is used by individual application tasks or threads. This hardware level separation serves as critical security and reliability function. If an application task stack overflows or becomes corrupted, the MSP remains untouched, allowing the OS exception handler to safely take control and recover the system. For a C developer working on bare metal systems, understanding when the CPU automatically switches between these pointers is essential for debugging hard fault exceptions. Okay, if you want to go into embedded system programming, and we eventually gonna go into it, I think. AI assisted visualization, the future of debugging. The emergence of AI augmented visualization tools like code confabulators represent the next frontier in mastering C. These systems utilize, that's what I'm talking, using animation. I was hoping it's gonna give me some animations too, but I have to use these tools to get it, but I'm not gonna use those right now because it takes quite time. I tried once. I'm gonna find a workaround and or I'm gonna make my own animations. It's not very important. The important thing is I understand the thing, what's happening, and I learned I think most of the important things, and I have to if I have to go to mastery level, I have to learn almost anything, the important things. These systems utilize large language models to perform static and dynamic analysis of code, automatically generating flowcharts and memory diagrams that evolve as the code changes. Unlike traditional debuggers that only show the current state, AI visualizers can provide predictive hints such as highlighting a line of code and showing an animated close frame of a potential stack overflow that might occur under certain input conditions. Okay, tool type. Step through visualizer. Oh, Python tutorial step through visualizer. Synchronize code and memory view of code. We're gonna skip this because these tools we can use to visualize. Try to visualize. I'm gonna use my notebook too. We're gonna do it when we're gonna do actual implementation. Right now it's all theory, I think. Pathological case study, the recursive factorial animation, the full grasp of LIFO principle and the mechanism of stack frames. One should analyze the animated execution of a recursive factorial function. Factorial for this example illustrates how the stack maintains a unique context for nested calls. Yeah, this is very good example, I think, to understand the call stack and how it winds and unwinds, I think. So step 1, main calls factorial for the frame is put onto the stack. Variable n equal to 4 is stored. Then the function determines it must wait for the result of 4 times factorial of 3. Factorial 3 gonna call factorial of 2, and the factorial 2 gonna call factorial 1, and if the n is 1, we're gonna return 1. Okay, so factorial 1 reaches the base case and returns 1, and it pops unwinds, I think, unwinds, I think. So the 1 gonna go to the 2, 1 times 2, and then the 2 gonna go back, return for 2, 3, uh, 3 times 2, which is 6, and then 6 times 4, which is 24. This sequence vividly demonstrates that while factorial 4 is waiting, its local variable n equal to 4 is frozen and inaccessible until the function it called have finished their work. Yeah, it's very good analogy. And alright, synthesis of best practices for C mastery. This the culmination of understanding stack and heap dynamics is the adoption of golden rules that separate noise coders from master systems programmers. The deterministic memory discipline, symmetric allocation, every malloc, calloc or realloc must be paired with exactly one free. In an animation, this ensures that every creation event in the heap is matched by destruction event. Yeah, every time malloc, calloc or realloc we use to create a variable or data structure, we have to use free for it. Afterwards, when it's used and it done its task, I think. Immediate nullification. After freeing a pointer set it to null, this acts as a visual dead end for the pointer arrow, preventing the catastrophic error of a double free or dereferencing a dangling pointer. The lifetime rule. Always ask, does this data need to live longer than this function? If yes, use heap. If no, the stack is safer and faster. Yeah, we have to ask, does this needs to live longer than the function. We need to use the heap region or not to store the data. Scope awareness. Never return a pointer to a local variable. Never return a pointer to a local variable. The animation of a function returning shows its stack frame being wiped clean. Any pointer to that space is now pointing at ghost memory that will be overwritten by the next function call. Yeah, but if it's that's how the ghost areas gonna create, and we lost track of that and we cannot free it if it's a heap. If we created that pointer using this, I think, utilizing the educational landscape. The mastery is also a product of leveraging high quality resources. Okay, YouTube channels. Okay, yeah, it's giving me some resources. I'm gonna go and look into it. But Meso Academy, Jennings lectures. Okay, my code school are universally praised for their animated approach to memory management. I have to go and look into it. I'm gonna go look into it to solidify it, but I'm gonna try to give an honest reaction. I'm not gonna go and do reaction video or something. I'm gonna learn from it. I think, in particular, is noted for its ability to visualize pointers and data structure as physical entities, making the transition from code to memory layout intuitive. For those pursuing kernel level mastery, Jacob Sorber provides an unparalleled look into low-level system calls like SBRK and BRK that form foundation of all higher level memory management. Okay. I have to switch from Windows to Linux too, but in order to do that, I have to first clear my work from where I'm working right now. I have to deploy the app, which I'm gonna do eventually, and then afterwards I'm gonna with, then after only that then I can switch to Linux and continue working there. So that's a bit of problem. That's why I'm on Windows right now. Jacob Solver. Hope I'm you know what? Nobody's gonna get my YouTube. Okay, so basic task point translate simple commands. Command line arguments, that's very important I think. Learn GDB. This is the basic one. Embedded systems, debugging C programs. Okay, so there are resources. I'm gonna utilize those resources, but data structures, threads, yeah, multi-thread programming. Yeah, you will see that's plus point right here. I'm gonna get some gist and try get the main topics, and then I'm gonna do some research on it on my own, so it's gonna be good. But right now it's very comprehensive. The distinction between the stack and heap is a fundamental architectural paradigm. The stack provides a high-performance deterministic environment for transient data, while the heap offers the flexibility required for complex persistent structures. Mastery of C is achieved when a programmer can move fluidly between these regions, utilizing each for its strengths while vigilantly avoiding their inherent pitfalls. As systems continue to grow in complexity, the ability to reason about memory at this granular level remains the most enduring and valuable skill in the toolkit of a professional software engineer. The shift toward interactive animated learning ensures that the next generation of C masters can see the memory before they ever write a single line of code. Yeah, to imagine where it's gonna store and how it's gonna go. Actually, people are using Rust for systems programming right now. It's not very good infrastructure, but actually I know C somewhat. Its syntax, I'm familiar with it. That's why I'm using and trying to learn with the help of C. That's the main point, and I can learn Rust also, but first I have to complete what I started. Okay. Should I take a quiz or something or not? I think so thank God no one is here. But it would have been plus point. Anyways, I think I should take a quiz, but I should have not. The next time I'm gonna do, we completed this. Next time we're gonna cover malloc, calloc, realloc, and free. We're gonna take these functions definitions and their implementation example. Then we're gonna try to practice on some using this. We have a thing for that too. So that's it, I think, for today. Okay. So 6 people. Oh, I don't know how to handle friends. I don't know. Okay, bye. Thank you very much for listening.